All right. So today we're going to continue with arc length in some sense, except now we're going to generalize it to another dimension. You guys will revisit all of this stuff in Calc 3. Arc length, area, volumes. You'll have much better techniques for doing it in Calc 3. At the moment, we're trying to use our Calc 2 techniques and use some of the basic geometry behind some of these shapes of how they're created, whether it's a revolution, whether it's a cross-sectional area, and start to develop these visual skills and see how we can compute a lot of these areas and volumes and lengths using just basic Calc 2 techniques. So our setup for this guy, what we're going to do is most of these that I've looked at, we're always going to be rotating about the x-axis or the y-axis, which is nice. I don't think a priori they have to be. We could still generalize these techniques if we were rotating about different lines, y equals 2, x equals 3, as we've seen with some of these volumes. But in general, what we're going to have is some curve. And then if we rotate this curve around the y-axis, say, we will, sorry, let me spin my paper to try to draw it here since I'm right-handed. That looks like a reasonable mirror. And we are rotating about the y-axis. And so we've got this kind of bowl shape, but in this case, we are not filling it in. We don't have another curve. We don't have a bounded region. We're not starting with an area. We're only starting with a curve, a one-dimensional object, and then doing this rotational process essentially adds another dimension. So we have this bowl shape, this infinitesimal bowl with this shape determined by the function. And what we want to do is to determine the surface area. So how are we going to do that? We do it similarly to how we did the volumes in some sense. We want to slice it up. And in particular, we're going to slice perpendicular to the axis of rotation. And what are we going to get when we do that? When we slice it up, we're going to get, actually, I should have made this a little curved. We're going to get these ribbons. Let me try to draw another one. Like this top ribbon. It's going to be a slice. So again, instead of having a solid volume, they're not complete washers. It's just the outer ring of a washer. Yeah. Thin ribbons. And we can approximate the volume of these guys, or excuse me, the area of these guys. Well, it's going to be the circumference times the length here. So let's write it as the capital S. So let's use capital S for surface area is going to be given by the circumference. And then now we got to be careful, because even though we're slicing up horizontally, we want to be a little more precise with surface area in that our slices aren't necessarily going vertically. These ribbon threads aren't necessarily vertical because of the shape of the function. So what we're actually going to have is the distance. Will give us a better approximation. So in other words, if we were to kind of blow these pictures up, what we have are these ribbons. But there's some infinitesimal shape here with the curve. And so this distance here is our infinitesimal piece of length. And of course, the circumference is 2 pi r. So this is our breakdown. And now if we want to compute our surface area, this tells us that our goal for these problems is to determine two things. One, we've got to determine the radius. However, at the moment, we also don't know this integral in terms of ds. We don't know quite how to work with, so we need ds in terms of either x or y. And of course, since we want all of the variables to match when we are integrating, we probably want to do this first. Find out what variable we want to integrate with respect to, so that way when we determine our r in terms of that variable, it will follow and everything will be consistent, right? We can't determine what r should be a priori if we're not sure which variable is appropriate. Now, nicely enough, we will almost always have y as a function of x or x as a function of y. And as you can imagine, as dictated by the direction of revolution, we do want to approximate these as dy's, but then scaled by our factor that we determined for arc length. Namely, we saw that our ds is the square root of 1 plus dy dx dx. Or conversely, we could have also solved this for 1 plus dx dy dy squared here. So let's see an example. Suppose we got a function y is equal to square root of 4 minus x squared. This is the top half or top part of a circle, but we're only going to go from -1 to 1, and we are going to rotate about the x-axis. So what's this look like? We've got a circle of radius 2. Tick mark's a little off. All my tick marks are a little off today. But we are cutting it only from -1 to 1. So it's like we're taking this top part of the circle here, and then we are rotating that around the x-axis. So we've got this thin, I guess not thin, but like this slice of a sphere and the surface of a sphere that we are rotating about the x-axis. And so naturally we are going to cut perpendicular to that. And have these thin ribbons that we're going to add up the area for as we move left to right. And so our surface area is going to be given by, let's see, I guess we didn't quite put those formulas together. We've got 2 pi r ds. And we need to figure out r and ds. And since we are slicing perpendicular to the x-axis, and we have a function of y as a function of x, we can see we want to at least approximate our ds's, the arc length for each of these pieces, by our ds function relative to x. So this guy is our ds. And we want to use this version of ds since we are slicing perpendicular to the x-axis. And so now we can just fill in the rest of our pieces. Let's go ahead and compute our derivatives. So dy dx is going to be minus 2x over square root of 4 minus x squared. So 2 over in the denominator there. 2's are going to cancel, so minus x over square root of 4 minus x squared. And then our dy dx squared is going to give us x squared over 4 minus x squared. Our R for these problems are always pretty easy. R in this case is just our Y. Give me 1 second. 2 pi x ds. I want to make sure I'm doing this right. Yep. So our R in this case is our Y value. I was having a brain fart there. For some reason, I was thinking that the R should be X, but nah, it shouldn't be. We're right. It's Y is our radius. And so what we're going to have to do is then plug in for our radius the function again. So our radius is square root of 4 minus x squared. And plugging all those pieces in. Let's see if we can do it here at the bottom so we can keep all of our work together. Our surface area is now the integral of 2 pi times the square root of 4 minus x squared times the square root of 1 plus x squared over 4 minus x squared dx. And then where are the bounds of integration? So the bounds are wherever these slices lie. We are cutting up perpendicular to the x-axis. And so our x's range from -1 to 1. Okay, so basic algebra. How do we simplify this? And then we can talk about the techniques of integration. Let's go ahead and rewrite it. Pull out 2 pi, and we had square root of 4 minus x squared times square root of 1 plus x squared over 4 minus x squared dx. How do we simplify stuff like this? Well, we are multiplying two square roots together, so we can multiply, we can move this term under this square root and multiply the functions together. And so we're going to have 4 minus x squared multiplied by 1 plus x squared divided by 4 minus x squared. All of that, I'm going to save myself some writing and just write that as to the 1/2. Sometimes drawing square roots can just get a little messy, and organizing your roots, especially if they're huge. And then things you can do, well, this term is not entirely nice. You might want to find a common denominator for those. The other thing you can do is distribute this factor as a whole into there. And the nice thing about that is this 4 minus x squared will cancel the other term's denominator. So when we simplify that, we will have 4 minus x squared plus x squared all to the 1/2. So nicely enough, since that term was the same as the denominator there, when they cancel, it gives us a fairly easy simplification. And so we've got 2 pi from minus 1 to 1. X squareds now cancel. And we've just got 4 to the 1/2, which will just give us a 2 dx. So we'll have 4 pi times x from minus 1 to 1. And we get 8 pi. Any questions? So that's essentially all there is to it. And these problems that we do, they're going to all look very similar. So let's do a few more just to get the hang of it. The real practice with these will be when you start doing them on your own. And let's just get a new piece of paper, since a lot of these problems are fairly lengthy. We do want to draw pictures, give ourselves space. So some other examples, we can have functions like y is square root of 1 plus e to the x. From x between 0 and 1. And let me double check on this one. Which way did we want to rotate? About the x-axis. So graphing these again might take a little bit of a work, as long as you can get the general idea of the graph for these ones. You should be all right. So we need 1 plus e to the x, and then take a square root of that. So e to the x has an asymptote at the origin. We're going to shift it up 1, so that'll shift the asymptote up here. We are going from 0 to 1. So it should be something like exponential curve. Of course, if we take a square root of an exponential curve, it's not going to make much of a difference. It's still going to look exponential. And so when we are going from 0, it should be square root of 2. So that should be a little bit higher. But that's all right. The general shape is the most important. We'll have something like that. And then we are going to rotate it about the x-axis. So we're going to have our shape look like this. So our y values, not terribly precise with how we're plotting and graphing. Getting the general idea for the shape is going to be most important. I would recommend plotting these. You can kind of just jump into the formula, in the sense that if we know we are rotating about the x-axis, we are going to want to slice things with regard to dx, so perpendicular to the x-axis. And we can just follow our formulaic chain. As we saw in our last one, the r, since we are rotating about the x-axis, the radius is always y. However, since we are rotating about the x-axis and cutting up essentially perpendicular to the x-axis, we want to integrate with respect to x. And so we chase out our pieces. Of course, we've got our function for y. And then we should probably compute our derivative and square it. dy dx, so we're going to have 1 over 2 square root of 1 plus e to the x times e to the x. And just like I did on the last one, I kind of like to do the squaring here. You could plug this in for here if you want and then do the squaring, but then you're doing that square underneath the square root with all the other junk in the integrand. Sometimes it's easier just to do the squaring and simplification on the side and then plug in the square itself for the squared dy dx squared underneath the square root. So when we square it, we will have e to the 2x over 4 times 1 plus e to the x, or e to the 2x over 4 plus 4 e to the x. So those are our pieces. Let's go ahead and write our integral. So our surface area now, integral of 2 pi, we're going to bring out our radius, square root of 1 plus e to the x, times the square root of 1 plus, now dy dx squared is just this term. And then we've got our dx. We can go ahead and find our bounds too. Our bounds, since we're integrating with respect to x, should be x bounds, which we are given 0 to 1. And now the rest kind of reverts to our algebra skills, simplifying this integral, and then our techniques of integration skills. So let's go through that again. Going to be seeing a lot of square roots in these problems. Of course, the square root appears in the formula. And so a lot of times our functions themselves also have square roots in them because we like it. Square roots play nicely within each other. So similar to the last problem, let's work this out and do some of the algebra here. And I'm going to write it as 1 plus e to the x times 1 plus e to the x. And actually, I'm going to go ahead and factor this 4 out again. And all of those guys raised to the 1/2. Don't forget that 1/2. That power of 1/2. So this helps us do our algebra. And of course, the reason I wanted to factor this 4 out is because we once again have these same factors. So when we distribute this guy as a whole between those two terms, we're going to get 1 plus e to the x times 1, and then plus e to the x over 4.
I think you might have forgotten the 2x on the numerator, or e to the 2x.
Yeah, e to the 2x there. I was going to say, this integral we can't do. Now it looks better. Now I think we can do it. So what's the trick to doing this guy here? Got to remember all your algebra tricks. We have something under a square root, right? Integrating square roots are a pain, as we've seen. Trig subs, you got to do fancy stuff with. And if we have functions that aren't quadratic underneath the square root, we're almost out of luck. So we've got, let's write it as 1/4 e to the 2x plus e to the x plus 1 all of the 1/2 dx. And so we should recognize this as a perfect square. Is going to be the way to do that. Two ways you can, if you're not comfortable with the 1/4 as the lead coefficient there, you can always pull it out. If you want to do a u sub here, you can as well. In this case, though, the u sub might look a little weird just because your differential isn't going to be able to work nicely, right? If I set u is equal to e to the x, we will have a quadratic here, but then we won't have a du. So you would have to do an algebraic u substitution to help you with the factorization and then undo that. So let's just write it and see how this should factor. 1/4 e to the 2x, if we consider that a perfect square, well, the square root of that's going to be 1/2 e to the x. Likewise, this one. 1's a perfect square. And so we can kind of check ourselves. What do we want that perfect square to be? Square root of that term plus the square root of that term. And then you can check that if we were to FOIL this out, our middle term would be 2 times this guy plus that guy times that guy, which would give us just e to the x. And so now, nicely enough, we've got a perfect square underneath that square root. Those will undo each other. And we have a much easier integral now. So it is a mental check, or at least a meta check, I guess we should say, in terms of problem solving. Whenever you're doing any of these, if at the end result of your algebraic simplifications, you get something that is not integrable or like really hard to integrate, double check your work, double check your drawings, double check your geometry to make sure you're defining your functions correctly. Though, of course, with surface area and arc length, fairly formulaic. We almost have to give you the functions, and then you know, check your calculuses, really check your derivatives, check your algebra are the things you're gonna have to check. With some of these work problems and more visual problems, you do got to check your geometry, and that can be hard, making sure you drew the picture correctly. Of course, the other thing is sometimes we do get to this end integral after we've done our simplification, and it could be a little complicated, right? We still could require more specific techniques of integration, whether a u sub, a trig sub, integration by parts. But you should also kind of expect that after a problem with this added length, the end integral, it shouldn't be, you know, a 4-step integral where you've got to do both u sub and integration by parts and then a trig sub. It would just be, that would be murder, and we don't want to murder you guys that hard. Okay, so I'll leave the rest of that integral to you guys. Hopefully everyone's pretty solid on that guy. Just straight up antiderivative, no tricks there. And then let's see, let's do maybe one more. And let's see if we can find one that is rotated about the y-axis. So our example, we've got y equals 1/4 x squared minus 1/2 natural log of x. X goes from 1 to 2. And then we want to rotate that about the y-axis. So this is a book problem. I'm not sure if we're going to be able to do this, or at least how easy this one's going to be. Because we're going to want to integrate things with respect to dy, but I don't know if we can actually solve for dy in this case. Well, let's take a stab at it and see what we can do. I think this one's going to be a little bit weirder in terms of how we are cutting it up, because we are still going to actually be thinking of our slices with regards to dx. Let's see. So first step, we want to graph this guy. How do we want to graph it? X equals 1. That'll give us 0. That'll give us 1/4. We are rotating about the y-axis. So our y at x equals 1 will be something like 1/4. At x equals 2, we will have 1/2 natural log of 2, 1 minus 1/2 natural log of 2. Not entirely sure what value that's going to be. So we're just going to draw a generic picture of a curve. It's going to be increasing, should be concave up. If we are thinking in terms of order of growth, x squared is going to dominate. Natural log doesn't grow very fast. So when we're subtracting off a natural log, it will make the function, it'll look quadratic, but opened more. It won't grow as steeply as a typical quadratic because we are subtracting off this term. But because this term grows very slowly, we're not going to be subtracting off a lot. So the overall shape is going to be determined by this quadratic part. So it should look something like a concave up curve. So this one we're going to have to do a little bit differently. We want to integrate, in some sense, we've got to integrate with respect to x still, even though the axis of rotation is about the y-axis. And why is that? So WRT means with respect to dx. Oh, sorry, that was off the page here. So we still have to integrate with respect to dx. Because we can't solve for x. So let's take a look at our formulas that we were deriving here. We can follow our same line of reasoning. This equation still holds, and our r in this case, again, was x. I forgot the squared here. So nicely enough, if we are using this version of the formula, namely integrating with respect to dx, even though we have slices perpendicular to the y-axis, the radius is just x. I don't have another function I need to substitute that, since that variable coincides with our differential. So how do we want to think about this then? Because it's a little counterintuitive to what we've been doing and how we've been integrating. The key thing is that the length of each ribbon isn't strictly perpendicular to one of the axes. Really what we've got going on is we can think of these ribbons, since they've got some curve, some diagonal, if you want to approximate it as such, as our ds, our little ds. And if we were to expand upon this ds side to draw it even bigger, just as we did with arc length, we derived this formula for little ds in terms of our Pythagorean theorem of x's and y's. So when we did the previous problems, well, we solved for this formula, the ds in terms of dx. And in the previous examples, by the axes of rotation, we were taking our ribbons and thinking of the ribbons growing this way, and then adjusting our formula for the arc length based off of where we were at in regards to that position. In this case, it is slightly different. You kind of just have to orient your brain a little bit differently and think, well, our ribbons are also growing horizontally, even though we're slicing vertically, so to speak. They are also growing horizontally. And every time I change my horizontal position, the arc length, the edge of these ribbons, is still growing according to the same formula for arc length. And nicely enough, though, at least now we don't have a function to plug in for x. So we can essentially leave it like this and now find our pieces. So a little counterintuitive in some sense, because by the way we've sliced it, we're kind of going along the direction of the slices as we add up, since we're still integrating with regards to dx. So let's go ahead and write everything out. We've got s is our integral now of 2 pi x times square root of 1 plus dy dx squared dx. And now the only pieces we need, we said our r was x, and we don't need a new formula for that since we are integrating with respect to x. Our dy dx, so we'll recall our y, 1/4 x squared minus 1/2 natural log of x. Dy dx, 1/2 x minus 1/2x. And then dy dx squared will give us 1/4 x squared minus 2 times 1/2 of x times 1/2x. So those will simplify nicely. Plus 1/4x squared. And so here we've got to do some algebraic simplification. This is why it's kind of nice to give yourself the space to just do the algebra and not having to have this underneath an integral. Sometimes some of the worst mistakes I've seen is, you do everything right, but if you're doing too much algebra at once, you can misread your own writing. If your work isn't well organized or don't have the space to write it out, and then you can just write something wrong, and then that'll perpetuate through the problem. Those are mistakes you don't want to make, because you're doing it right. You just kind of like misread or missaw something, especially during an exam or something when your anxiety is a little higher. So let's see, those two terms will cancel. We've just got a 2 plus a 1/4x squared. Okay, so that looks about as simplified as it'll get. We did want to expand everything out because we are going to have to add that 1 to it. And so let's see how that throws things off and see what kind of algebra we need to do from there. We've got our 2 pi x, could have brought the 2 pi out. We've got a square root of, so dy dx squared plus that 1 is going to give us something similar. Just by changing that constant there. Now the question is how do we integrate something like this? What should our bounds be? Bounds were given in the problem, 1 to 2.
I have a quick question.
Yeah.
What happens to -2 and why is it -1 now?
We added that 1.
Oh, whoops.
Yeah, I just did kind of 2 steps in once there. I substituted and added that 1. I didn't want to have to write both of those steps out.
Should it not be a 1/2, a -1/2? The 2. I mean, before, like, initially calculated it to be 2.
Which one? This one?
Yeah, that one. Am I looking at it wrong? Because it's 1/2 times 2.
Did I miss that? Did I miss the, oh, those 2's are both in the denominator. Yeah, good. I was going to say something's not going to work out nicely for us. So we will have a 1/2 there. Actually, that works out way better for us. Thank you for that. I was confusing one of those 2's in the numerator and thought those 2 terms canceled. Yeah, so we've got 2 factors of 1/2. which will give us a fourth times 2. So a minus 1/2 here for that middle term. And that actually saves us a lot, because now when I have this as our y squared, when we add 1, we kind of do this same algebraic trick that minus 1/2 plus 1 gives us positive 1/2. As I was saying, algebraic mistakes are probably the easiest ones to make in these. And even when you try to keep organized, sometimes you overlook something. And that helped us a lot. Why did it help us a lot? What do we have here now? Now this guy, essentially the same as this guy, except with a positive 1/2. And this guy we know came from a perfect square. So this guy is itself a perfect square. So this will give us 1/2 x plus 1/2x. Quantity squared. And now the square root and these squareds will undo each other. And so, of course, we're left with now an integral that's doable. 1/2 x squared plus 1/2. And that guy should be easy enough for you guys. So any questions on these? We had a question in the chat. Is it right to think that you can use dy dx because it's concave up? Not necessarily, because it could be concave down and we could still use dy dx. It's really just the way we want to think about it is you really want to think about it generically in terms of just this 2 pi x. The radius is given by x and then times ds. Let's use a different color. Like our radius here is x, but ds is part of a curve. So this ds itself depends on both x and y. And so we have a little bit of a choice of how we want to describe how ds is changing. And so even if this curve were concave down, we would still get a similar picture. And this Pythagorean approximation, dy squared plus dx squared is ds squared, still holds. And so we have a choice there of how we want to describe the s. We can solve either in terms of dx or dy. And we are forced in this case, because we cannot solve for the function in terms of y, we have to use dx. So we still can use that same formula. dy dx, 1 plus dy dx squared, all square root, times dx is our ds. Does it always work? Yeah, these should always work out. If you cannot solve for y, you can always do it like this. This is kind of what I was saying at the beginning. These types of problems, they are very formulaic. So once you have the pieces, you can always fill it in as such. Of course, the way you want to determine whether you're doing dx or dy essentially just depends on the function that you're given and the curves and how you're given them. Of course, if we are given a different function with x equals some function of y, well, if I can't reverse that, we'll still have to use, where we might have to switch our integral now to a dy. So dx over dy squared there, and then dy. That x is still going to be x, which means we would have to plug in the function solved for x in terms of y. Does that make sense? Good. Yeah. So you really just have to make sure your variables are consistent and do a little bit of like meta problem solving in the beginning and determining which way you are forced to do it, which differential you are forced to use. And then try to pick out the pieces of the problem that you need to be consistent with that. All right. So let's continue. Basic physics laws, just to kind of introduce some of these concepts. It'll give us a little bit of time on Monday to jump more into some of these complicated problems. Physics laws, just a refresher if you haven't had physics in a while. Primary one we're going to be using, physics and engineering. Key physics we're going to be using, we'll call it baby physics. This is when you first learn physics and algebra based. Work is force times distance, and I don't want to use D, so I'm going to call it delta S, or little s. So our little s is our position, right? So the change in position is our displacement. Of course, we've also got force is mass times acceleration. So those are the key things we're going to start with. We want to now move on out of baby physics to, I don't know, maybe toddler physics is what you want to call the next stage when we get into calculus. And so what we want to do is sort of redefine these laws. We'll say it kid physics. Our work is going to be the integral of dw. And so what do we mean by our dw? It is the infinitesimal amount of work we are doing on each piece of the system. And this piece of the system is going to vary depending on the situation. These questions get a little bit more varied than like the volumes that we've been looking at. These volumes and slices in regards to areas still play a role, but now we've got some physics laws we also kind of got to throw into the mix when we're doing these work problems. The most common thing we're going to see is that we're going to have some force, generally as a function of x, and then we are going to be slicing up the distance. So this force depends on x. It's going to change, varying as we move through space. And then so we are essentially slicing up our space, the distance we travel, into infinitesimal pieces, and then measuring the force on that infinitesimal piece and adding those up as we move the object, as we move these pieces through space. Sometimes I like to write it as df times x. There are certain cases that are going to arise where it's almost better to think about it as our object itself, we are slicing it up, and there's going to be, we want to sort of measure the infinitesimal amount of force on each piece. And then the distance traveled is generally constant and just varies as x. So as like a basic example, let's say we've got a kid that walks up a slide and goes down the slide. So let's say he's something like 50 kilograms. Walks up, let's say 3 meters of stairs. What is our work done? In this case, we can use our baby physics methods. And why is that? Well, our force is relatively constant. So let's actually pull in our pieces here. What is our force? Force is going to be mass times acceleration. And even this one, we might actually break down into infinitesimal pieces, especially if we have infinitesimal pieces of force in this situation. We'll see those as we get to them. But in this case, the mass is constant. What is our acceleration? Our acceleration is gravity. So 9.8 meters per second squared. For most of the problems, we might just leave this as g. Since we don't like to compute decimals, we do want to see all the work done by hand. We can keep constants as they are as just g. And so kilograms times meters per second squared is newtons. So we can call this 50 g newtons of force. The work done in this case, of course, we're going to recover our basic algebraic formula since we are just integrating a constant. And we should say that our change, our displacement, if we walk up 3 meters, if we consider the ground 0, and of course we walk up 3 meters at a height 3, our top will be 3 meters. And so we are just going to get 50x, force times distance, and then we will recover the displacement there. So we will get 150 Newton meters of work. I think Newton meters is joules, yeah? So for slightly more complicated system, we want to see, well, what happens now if I don't have a constant force? So the easiest example we like to start with are springs. So let's just introduce it, and then we will finish this problem on Monday. So suppose we have a spring and its natural length is, do we want to use meters? I know some of you guys, or at least one of you guys, is in the UK and doesn't want us to use imperial units. We use centimeters, 10 centimeters. Natural length. Well, we all know how springs work. If I pull on the spring, it's going to pull back. If I try to compress the spring, it's going to push back. And moreover, the further we stretch the spring, the stronger the force. So we'll say the further the spring is moved from equilibrium, the stronger the force. Namely, this is Hooke's law. That the force on the spring is equal to Kx constant K, our spring constant, often what we call that, and then x is the distance from equilibrium. So naturally, what we're going to have to do is, in these problems, is one, we need to figure out the spring constant for a given situation. So oftentimes we are given something like to hold the spring at 15 centimeters. Requires 40 newtons of force. And then what we want to know is how much work is done moving the spring or stretching the spring from 15 centimeters to 18 centimeters. So this is our information about the force on the spring. We're going to use that to deduce our spring constant. And then now our question is asking about work. So we're going to use our work equation. And in this case, we want to use a non-constant force. So our force equation determined by the distance stretched. Any questions? All right, we'll continue this guy on Monday and get more in depth with these guys. We'll have a lot of different examples. We'll have pulling ropes. In this case, whenever we're pulling a rope up a building or picking up a rope from one end, it's one of those situations where it's almost better to divide it up into DFs, infinitesimal little pieces of force that you're pulling up from each piece of the rope. And there's also pumping problems, pumping water out of a tank, and hydrostatic pressure, which can get really tricky. So we'll focus on all those next week.